Okay, students, welcome to the third and final video for topic D2, stellar characteristics and evolution. And indeed, here I am going to talk in detail about stellar evolution. And in order to understand the evolutionary paths of stars on the Hertzsprung-Russell diagram, for example, we need to understand a little bit about what's going on in interstellar space, okay? Now, contrary to popular belief, the density of interstellar space is not zero. It's not a vacuum. Turns out that the density is equivalent to about one hydrogen atom per cubic centimeter, okay, which seems like a lot actually because there's a lot of cubic centimeters, but really this density is about 10 to the minus 21 kilograms per cubic meter. And this results in a temperature of interstellar space of not, of course, absolute zero, but anywhere from 10 to 100 Kelvin. It's really cold in space, all right? This stuff is mainly hydrogen and helium, okay, 74%, 25% roughly by mass, all right? The point is that when this stuff, which is hydrogen and helium, gets compressed, a star can form. And you need some force to start the compression. Maybe an exploding supernova or some other sort of cosmic collision between two massive things. But once this is started, it will continue naturally as the gravitational forces of the particles pull each other together. As the atoms are pulled together, they gain kinetic energy, so therefore they gain temperature, and the pressure increases, okay? And this pressure, which is called the radiation pressure of a star, acts outwards. So you have a sphere of atoms, okay, with a radiation pressure acting outwards because of the kinetic energy of the atoms, but then you have enough atoms that mass starts building up and you have a gravitational force. When the radiation pressure equals the gravitational force in magnitude, you get a nice big ball in space of atoms, which is what becomes a star, okay? Now, as the atoms get closer together, the gravitational force increases, so the gas continues to collapse, pulling in more and more hydrogen and helium from the surrounding interstellar space, which further increases the mass. And all of it gets hotter at an increasing rate, okay? Now, as the temperature and pressure increase, the core contracts, it gets tighter and tighter, and a rotating sphere of superhot gas forms in the core and becomes luminous. It starts giving off photons. And this is called a protostar, okay? So protostars emit photons, but they're not visible through the cloud of gas surrounding it for about another 10 to the 5 years, okay? So that's a lot of years, that's 100,000 years. After about 100,000 Earth years, the radiation from the protostar blows away the dust cloud and the star shines nice and brightly from the inside. Now, at this point, it's relatively massive and luminous and becomes what's called a Premainsequence star. Remember how most stars, 90% or so of all the stars that we can detect, are on the main sequence, okay? This is before it gets to the main sequence, okay? So it's going to be to the right of the main sequence in the HR diagram. And I'll show you a diagram in just a minute to show that with arrows. Now, the core continues to contract and heat up until nuclear fusion takes place and nucleosynthesis takes place, which we've studied before, okay? So once fusion starts, it heats up even more, causing higher pressure, okay, radiation pressure, so which balances the force of gravity, so it stops contracting. Once that happens and the size of the star becomes more or less stable, it becomes a main sequence star, okay? Now, this nucleosynthesis of hydrogen into helium takes a lot longer than any other star process. So that's the reason why a star spends most of its life along the main sequence where nucleosynthesis is taking place, and you have that the radiation pressure is about equal to the gravitational force, so the diameter is fairly stable, okay? Now, from the Hertzsprung-Russell diagram, L and T change, right? So the position on the Hertzsprung-Russell diagram can change, right? So it's the mass of the star. This is a very, very important concept for you to remember. In all of stellar evolution, it's the mass of the star that determines ultimately what happens to the star, what evolutionary path it takes, okay? So for example, the core of a small star never gets that hot. So as the radius goes down, the luminosity goes down. A star that's about the size of our sun, okay, has a relatively small radius, but the temperature is constant until the outer layers lose their temperature. And a large star's luminosity stays more or less constant. So as the temperature goes up, the radius goes down, okay? We'll talk a little bit more about that. Now, for stars on the main sequence, the mass and luminosity are related by this relationship. So L is proportional to the mass to this alpha, where alpha is this variable placed between 3 and 4. Okay, we don't actually know, scientists don't actually know the precise value of alpha, but in your IB data booklet, what we do is we basically assume a value between 3 and 4 at 3.5, and that generally works in calculations. Remember also that luminosity is similar to power. It is power. It's energy over time. So that's mc squared over t, okay? Which means that mc squared over t is proportional to alpha times a times t to the fourth, okay? Which is proportional to, or equals, which is proportional to m to the alpha, okay? All right. Now remember, we're talking about two different alphas here, by the way. It's a little bit confusing. Anyway, assuming an alpha of, say, 4, which is not what you're meant to do in the IB, you get that t is proportional to m, the mass, to the minus 3, okay? So what that means is that the lifetime of a main sequence star is proportional to the inverse cube of its mass, which is kind of interesting. You don't really need to know that for the IB, but it's fascinating how astronomers can deduce these kinds of things from these kind of esoteric equations, and things that we're never going to be able to really observe them directly or measure them, right? Pretty amazing TOK implications here. All right, so here's an example of a problem that you might want to do, that you're going to be asked to do on the IB exam, okay? They give you a Hertzsprung-Russell diagram. They will not give you one in this much detail, but they'll give you one with the basics on it, okay? And they want you to use the diagram and the mass-luminosity relation to estimate the ratio of the density of Altair to that of the sun, okay? So I give you a couple of minutes. You can pause the video and try this one. You have all the pieces that you need to solve this problem right in front of you. Okay, from the HR diagram, note that the sun and Altair have about the same radius, so they have about the same volume. My subscript A refers to Altair. The solar, obviously V with the circle and the dot in it, is refers to the volume of our sun. Okay. Now, from the Hertzsprung-Russell diagram, the luminosity of Altair is about 10 times. It's about 10 times that of the sun, roughly. Okay. Now, the ratio of the luminosities, LA to luminosity of the sun, is going to be MA over M mass of the sun, all to the power 3.5, okay? And then what you do, if you're asked to find the density, all you have to do is find the ratio of the, and I didn't include my little a here, right there and there, you just find the ratio of the masses, and the ratio of the masses is about 1.9. So that means that Altair, because they have about the same volume, Altair is about 1.9 times denser than our star. Pretty cool, huh? Okay, all right, remember, protostars begin to the right of the main sequence and move towards it, okay? And this diagram, which is from your textbook, all right, shows the relative paths, relative times it takes for different masses of stars. Okay, remember I said it's the mass of the star that determines everything, its stellar evolution. After about 12% of its hydrogen has been used up in fusion, the radiation pressure and gravity balance becomes disrupted, okay? And then the star moves away from the main sequence, okay? Now, to determine the path of the evolutionary path, the star's mass again determines its final fate. And here's a table from your textbook, which you do not need to memorize, but you do need to be familiar with this, okay? And we'll become familiar with it throughout our problem solving, okay? Now, moving off the main sequence, let's talk about what happens when a star moves off the main sequence. I'm going to talk about two cases. Number one, the first case is going to be relatively low mass stars. And I mean stars that are less than about 8 solar masses, okay? What happens is this, okay? So helium collects in the star's core, and it's surrounded by 2 layers of hydrogen. You don't need to know the great details of this, okay? But eventually the core becomes carbon, and the outer layers shed, and the star becomes a planetary nebula, which is a really beautiful thing that looks like that, okay? The star goes towards the upper right-hand side of the HR diagram, and it becomes a red giant because it's bigger, cooler, and a redder color, all right? Now, remember, a star spends most of its lifetime on the main sequence. The time taken to reach planetary nebula stage is relatively short compared to the amount of time that it spent on the main sequence. At the white dwarf stage, the star is essentially dead. So again, what the star does is it goes off the main sequence over here to the right-hand side, upper right-hand corner, and then it will end up circling around and end up down here. These are for low mass stars, relatively low mass stars, about less than 8 solar masses. They make this sort of counterclockwise journey, if you will, through the HR diagram, okay? Now, once it becomes a white dwarf, no more nuclear reactions take place. That's why I referred to it as being dead, okay? Electrons behave as a gas, and what they do is they generate something called the electron degeneracy pressure, and that keeps the star from collapsing under its own weight. So there's still a pressure acting outwards now, but that's also why it's small, is because electron degeneracy pressure is not as much as the chemical, as the pressure, or as the temperature, as the kinetic energy, that sort of pressure acting outwards from the higher temperature, okay? So a star will become a stable white dwarf if the mass of the core at this point is less than about 1.4 solar masses. And this is called, and this is something you need to understand, that you need to know qualitatively in the IB, it's called the Chandrasekhar limit, okay? And it's stable because electron degeneracy pressure balances the gravitational force, but at a much smaller radius, okay? All right, so here's a couple of diagrams showing you the relative sizes of a white dwarf. Okay, that is really small. Imagine about the mass of the sun concentrated into that sphere. Okay, we're talking about a pretty high density, right? It's about the size of the Earth. Okay, now case 2, what about higher mass stars? All right, for higher mass stars greater than about 8 solar masses, it's a different scenario. Okay, it's similar to low mass stars, except now the greater mass causes enough gravitational pressure to form heavier elements, and eventually iron is produced. So all the iron on Earth came from inside higher mass stars, okay? And when the iron is produced, iron is the final element, the final heavier element to be produced, and it stops there. So the star moves again into the red supergiant region of the HR diagram, okay? Kind of over to the upper right-hand corner. The core is very hot, and eventually the star explodes in a supernova. And the temperature drops dramatically very quickly, and the star collapses. And this is what a supernova looks like. Again, some of the most beautiful things you can imagine are way out in space, okay? Now, at this point, the core, which is made up almost entirely of neutrons, gets left behind, and it's greater than 1.4 solar masses in opposition to the case before, and this becomes what's called a neutron star, which an artist's rendition kind of looks like this. Now, a neutron star will remain stable from neutron pressure as opposed to electron degeneracy pressure if the mass of the core is less than about 2 or 3 solar masses, all right? And this is referred to as the Oppenheimer-Volkoff limit, which you need to qualitatively understand and know in the IB. If its mass is higher than this, it may further collapse and become a black hole. And a black hole, we've talked about that a little bit in class. Black holes are typically about the size of Manhattan, and crazy things happen inside and around black holes. So again, you need to know qualitatively this table in terms of how the initial mass of a star determines its outcome.